Okay, so welcome back to System Software. We are getting into the compiler project and how we can write a compiler for this language we looked at last time, this language called Simple IR, IR for intermediate representation. It's like an ultra simplified version of C, or you can think of it as kind of a high-level version of assembly. So there's only one operation at a time, there's no registers, infinite variables like in C, no math expressions, no control flow constructs, just gotos and conditional gotos. And today we're actually going to start looking at how we can translate this simple IR language into assembly. That's the job of our compiler, right? Is to take an input language, our source language, and translate it to machine code to be run on our actual bare metal. So questions from last time? Questions about the project? Questions about Interpost? Okay. All right, let's go over homework. All right, so the question was, write a function in simple IR that computes the nth element of the Fibonacci sequence. Input a number as a parameter and output the result via return. Oh, that's kind of painful. So that's the question. Who wants to see me actually like code it up? Oh, darn. Okay. Now I actually have to do it. All right. So let's make a function called function fib. And yeah, correct me if I'm going to do this from like memory because I want to try to, yeah. All right, so compute the nth element of Fibonacci sequence, input a number as a parameter, and output the result via return. So we're going to need some local variables. We have the number as the parameter. I'm going to call it n. So there's going to be a local variable n at least, and there's going to be some return value. I'll just call it retval for now. So here's our like Fibonacci like function definition. We've got, it's called fib, takes two local variables, so far has two local variables, takes parameter n and returns a return value. And what is Fibonacci sequence? Let's see if we can remember what this is. So sometimes it starts at 0, sometimes it starts at 1. Let's just start at 1. So notice, since I'm doing this totally fresh and I didn't prepare to do this homework and I don't think I have the answer written somewhere. So I use comments extensively, so I'm going to comment ahead of time before I even write code, just so I can make sure I know what I'm supposed to do. Is this the Fibonacci sequence definition? Does that look about right? Okay. So we're going to need a couple of conditions here. We're going to need to check whether n is 2 or less. So if n is less than or equal to 2, then let's just save the return value to be 1. Oh, sorry, that's not right. The first two elements are 1, not so. And I guess if you want to be really like error checking, you should check if n is like less than or equal to 0. I'm going to like not do that. So we're going to just like assume n is greater than 0. All right, so we're going to do it that way. And now you want to do this iteratively or recursively? Or who did it recursively? Who did it iteratively? Recursively? Recursively is probably easier, right? I think recursively is the easier way. So yeah, so if n is less than or equal to 2, and if n is greater than 2, then we're going to have to call fib on n minus 1, call fib on n minus 2, and and then the return value is going to be, I'm going to call this n minus 1 plus n minus 2, and then return that. Does this seem like reasonable pseudocode? Did I make any mistakes in pseudocode? All right, so let's try to implement each of these. So remember that if we want to like run code based on a condition, if we say like if go to n less than or equal to 2 and put retval here, well, it's going to skip that code. So you could do this a number of ways. So you could either invert the condition like I'm going to here, or you could keep that condition and add some extra branching. So I'm going to try to keep this, well, let's invert the condition. So if n is greater than 2, then go to, let's just call it n greater than 2. So if it's not greater than 2, then we're going to run the next line of code. If it is greater than 2, then that's the other side of our condition anyway. If it is greater than 2, then we got to do this pseudocode. Now I'm going to leave this off for a second, just assume I got it right, and make sure I've got this if go to correct. So if n is greater than 2, I want to jump here and run the do the recursive stuff. Otherwise, I want to run retval equals to 1. And so I already have return retval. So here's the comments here. So notice there's one little problem here. If I don't jump to ng2, my ng2 branch, and I run retval, well, if I don't do anything else here, I'm going to run all of this code in ng2 regardless of what the condition is, right? So I'll either skip retval 1 or I won't skip at retval 1, but I'll always run this code. So I can avoid that by skipping past this part of the code by making a new label. Questions about that? So this is I didn't actually show the translation of this last time, but this is the classic structure of an if-then-else statement in the assembly language. So if I've got a C program like this, I'll just call two different functions here. Then the way this gets translated into a language that doesn't have control flow, that just has branches, it would be, and I wanted to like preserve this structure. So this is kind of like a mix of C and assembly. This would be my else branch, and this is my if branch. You only want to run one of these branches. You don't want to run both. So if we don't have this go-to here, then the if branch and else branch would both run. You see what I mean? So if that's not here, if we're starting at F, we're always going to run G after F. Does that sort of make sense? Hey, this kind of like parallel structure here. So this is with the translation of an if statement. So you're not going to have to translate this in this class. You can take like graduate compilers class to see more into this translation. But that's the logic of the translation. So here I would invert the logic. So I only branch if I want to go to the else condition. Otherwise I go to the if branch and then skip past the else branch. All right, anyway, so that's the same structure I have here, where I've got this. I mean, it's the same. It's really the same code here. Okay, so then I need to implement this code here. So this is the branch for if n greater than or equal to 0. So we need to call Fibonacci on the parameter n minus 1. So let's call this fib n minus 1 and fib n minus 2. So I need to compute n minus 1 and n minus 2 because I can't do math expressions, so I have to, and I can't put math expressions in function calls, so I have to separate all these out into their individual operations. So this will be call fib on n minus 1, and this will be call fib on n minus 2. Questions on this code here? So I'm just computing what the parameter is and then making the function call as separate operations. Much closer to what the machine code will look like. So there's, well, let me clean up this commenting. So there's the call to fib n minus 1, there's the call to fib n minus 2. And now I need to set the ret val to be, actually this code is correct actually already. All right, and I think that's it. Questions on this code? Let's see if I actually got it right. So I'm going to build the compiler, and then just to punish myself a little more, I'm going to run it. And I got some errors. Line 9. What did I get wrong in the syntax on line 9, or is it this stuff? Did I get the right wrong comment? Oh, it's not if go to, it's just if, right? I think that's it. Okay, that ran, it ran, so I mean, we could actually run it and stuff, but I need to set up like a main function and all that, so I'm not even gonna run it, but here's what the output, should look like if you were to translate it. All right, any questions on the homework? It's a little bit more tedious, but it's really like an assembly programming exercise, yeah. In which language? Simple IR. The language, as I specified, does not have arrays. Yeah, but you could simulate them, finite arrays, by having multiple variables. Oh, I did forget one thing. I forgot to add these variables here. So actually, this is a little bit wrong. I forgot to add all the local variables that I have here. So nm1, nm2, fib, nm1, fib, nm2. Or you could still call malloc because we're using the same C toolchain. So you could call malloc, get a pointer, and then work out some, actually kind of work out some, because you can use pointers in this language. So you could have heap arrays. Oh, you called malloc on the homework? That's a little bit outside the scope of what we're doing, but yeah, you would just call it and you'll get a pointer back as a return value. And then you can do pointer arithmetic on it, but it's tedious to do it that way. But yeah, come to office hours and we can like walk through it. All right, so that's homework. Any other questions on homework, Simple IR, the compiler project? Did everyone do all the reading, Antler, and the CodeGen stuff? Looks like everyone totally did. All right, let's do attendance. Okay, so let's go over what everybody knows how to do, but we're going to go over how to translate between two languages for performing arithmetic. So the goal of this part of I guess I should say about the project. The project is separated into three parts. The first two are arithmetic and branching. Second one is for pointers. You can see that here. And the third one is for supporting functions. So today and next week, we're going to do cover all the stuff you need for the project, but all this material is online. CoGen handbook is online. The project is assigned, so you can. I'd recommend starting soon, because it is tricky to just keep all the stuff in your head when doing the compiler, even though the translation is pretty simple, but just kind of managing it all in your head is a little tricky. Okay, so our goal here is to take simple IR arithmetic operations like this, where we have a variable on the left-hand side, which is going to be the destination to store the data, and then 2 operands and 1 operation. There's no math expressions, it's only 1 operation at a time, and that's way, way easier to do translation to assembly, because assembly similarly takes 2 operands and 1 operation at a time per opcode. Okay, so questions on the goal? Kind of makes sense, right? So you can already see that it's like very close, right? Syntactically, you can imagine sitting down and maybe writing like sort of brute force, spitting out some string manipulation code to do this. But let's look in detail at how to do this. So this is just the piece of the simple IR grammar that defines what an assignment operation looks like. So this is the syntax. So it defines what all arithmetic operations will look like. So it's a name followed by this exact string symbol, this colon equals, followed by an operand, which is either a name or a number, followed by an operator, which is one of these 5 symbols, plus, hyphen, asterisk, /%, and operand 2 is also either a name or a number. So that's what this pipe symbol means, or effectively in the grammar. So you don't have to worry too much about the formal grammar, but as long as you know intuitively that the shape is always string for the variable, and then 2 operands and an operator, that's all you need to know. So yeah, that's exactly what it says here. So name is for the assignment, then you have 2 operands and an operator. Operands can be integers as well, and we've got 5 operators available. These correspond to add, subtract, multiply, divide, and modulo. Just like in C, they have the same meaning. But remember, these are just ASCII characters. They don't have any meaning until our program gives them meaning, in this case by translating them to assembly. So questions about arithmetic operations in simple IR? Okay, so we quickly went over last time how variables are handled at the assembly level. So if we have a string like x, can we address memory at the architecture level using the string x? No, right? So how do we address memory or state at the hardware level? What's that? Yeah, that's actually how we did it. We did offsets. Offsets from a location in memory. So, RAM is just a contiguous sequence of addresses. And when you want to access some space in RAM, you give it the address, you give it the number. Or you give a register if you want to have data stored on the CPU. So it's like the memory hierarchy, which I think you should have learned about in computer organization, right? Memory hierarchy. Okay, and so this, when you see a statement like this in simple IR, it corresponds to a sequence of, or a set of, or a mapping from the variable name to an offset from a location in memory. Does anybody remember the register that holds that location in memory of the array of local variables? So last time we went over how memory is managed for a function. So there's a special register, special purpose register in the Intel world called RBP. The R just means 64-bit, BP means base pointer. So it's the array effectively that holds all of the local variables. So you can think of it as just a pointer, an array, pointer to the beginning of an array that holds all the local variables. And then the local variables are stored in slots in this array in memory. And so just like in C, when you give an offset, that's basically just adding to that address effectively to find each slot of that array. And so this RBP works much the same way. Questions on that? Was that kind of clear last time? So this is how we're going to manage memory for our local variables in our compiler, how we're going to generate code to manage that memory. So recall that local variables, and we'll see how this actually gets implemented when we get to functions, but you just kind of have to believe for now that there's this register that's just going to be there for you, that's going to have the address of the local variables. So those local variables are stored in the address, and each symbol name from that local variables list will be associated with some offset from that memory, basically some array element in that RBP array. So this is the C-like way of saying array indices, but this is the assembly syntax. So whenever we have a local variable access in our simplified compiler, this is the syntax for accessing that memory location, the actual memory location at runtime for that variable. So the AT&T syntax for this puts the offset first, and then in parentheses we put the register that holds the address of that array-like thing. Questions on that? Does it kind of make sense? So if we want to load variable A into some register, into register RAX, this is what the instruction will look like for our program. Because for the program we had local variables, -24 was the offset for variable A. And remember that in the Intel or the AT&T syntax, the destination register is on the right. So this is saying take the data at this address, given at this address, and store it into register A. Questions about that? So this is how we'll access a variable operand. We'll pull its data out, put it into a register. Questions? Questions on this? Yeah. Oh, that's a really good question. Does it matter the kind of data? Your RAM. What kind of data, I guess, basically physically, what kind of data does your RAM store? The RAM, each slot. Yeah, so at least in the architectures that we're using in our machines, they're byte addressable memory, so each address corresponds to 1 byte. What kind of data is that? Or what is it, how is it represented physically? Or what kind of data? Yeah, it's binary data, right? So it's just like high and low voltages. ASCII, how is ASCII represented? Behind the scenes. Or okay, how are integers represented at the machine level? In binary, right? What about characters, like ASCII characters, how they're represented? What's that? They're binary, yeah. What about like movie data, a movie file? How is it represented? It's binary. It's all binary data. Always binary data under the hood. So those data types, those are almost notes for us, the programmer, that constrain what kind of data it is or define what kind of data it is. So no matter what you say in your compiler, this is a string, this is a movie file, whatever, at the end of the day, it's all binary data. So at the architecture level, and you notice that assembly has no typing. It's just moving. The only type here is that this is a 64-bit number because we're in a 64-bit architecture. So we're just moving around binary bits, and at least at the assembly language level, there's no explicit specification of what kind of data that is. So that's a good subtle question. That notion of data types is effectively created by the language, the compiler or the interpreter. So that's a really good subtle question, because that, physically it's all just binary data. Even the representation of an integer is a decision because you have like signed, 2's complement signed integers, you have unsigned integers, you have not 2's complement integers, which I don't think any architectures use. So this is, again, the map territory problem. Binary data is just like high-low voltages. And the meaning of that is given by some interpreter. So in this case, if we use an add instruction on this data, we're implying that it must be an integer because it's an integer add. If we did a floating point add, we would get a very different result because floating point representation is different from integer representation. So here the move operation is really just copying the binary data, the sequence of voltages that are in RAM to a register. That's all it's doing at the low level. And so you can already maybe start to see a little bit how the compiler, the language implementation, is providing a definition of what it means to say the letter A. So if we say the letter A here in local variables and then we use it somewhere, that has a physical meaning of retrieving from memory the location associated with A and storing it in a register. Does that sort of make sense? So we're actually like giving meaning in terms of this machine, which doesn't have variables, it doesn't have the plus symbol. We're giving meaning to these kind of arbitrary ASCII symbols in terms of machine operations. And that's how we're defining a language. Okay, good settled question. Other questions on this? Any like technical questions on this? You just kind of have to get used to the syntax. This is just the syntax given to us in our system tools. Yeah.
When writing the project, how do we know like what the offset is?
Oh, that's a good question. I'll show this more when I get to the project. I've given you the code to do that. So for this compiler, because there's no data types, all the data types have the same size, I've just given you code that will create this symbol table for you. So given the local variables statement, it will create this table for you. And so you'll just do a lookup into the table. It's a little annoying to do the memory layout. You have to like do some assembly operations to do it. You have to make sure things are like aligned properly and padded properly. It's a little annoying to get right. So I've just given you code that will generate the assembly to do that for you. And then you just have to do symbol table lookups to get that offset. But the code is there. We can go over it and take a look at it yourself. You can see it. It's a little annoying, but it's just spitting out assembly operations. Okay, so that's how we access operands. The meaning of operands in our compiler is load from memory. And so that's really what variables are, right? Variables are storage. They represent storage. Integer constants are a little bit simpler, so we just have a move immediate in the x86 world, just like in MIPS. This is how you do move immediate. You prefix in the AT&T syntax. You prefix what is really the ASCII digit with a money sign, and in this AT&T syntax, that means immediate integer value. So what state will RBX have, or what integer will RBX have in it after this code runs? Yeah, it's the obvious answer. Yeah, it's 1. It'll have 1 in it, right? Just making sure you're awake. So this is how you do move immediate. So this is the meaning. This is how we interpret the meaning of constants, constant operands in our language. We interpret it as a move immediate into a register. Questions on this? Is this hopefully pretty straightforward? Hopefully maybe some MIPS flashbacks are coming to you. Okay, so what about assignment? So using an operand we loaded from memory, what does assignment look like at the machine level? Or how might we model assignment at the machine level? What's that? Move, yeah. So more specifically, store. We're storing. Though in the Intel world, move is used for lots of different operations that MIPS has different names for. But what assignment is in our compiler is just storing data in the memory location associated with that variable. So if we're storing a value for b, the variable b, and it has offset -2, then a storage operation, assignment operation, will look something like this, where we move some data into the memory location. That's a store in the x86 world. So move does store, immediate load, load. Questions on this? So we've already seen, 3 different operations for move. And then arithmetic, we just have a mnemonic for the op add. So remember from before that the destination register is here on the right, and this will move or copy whatever. This will take the values that are in RAX and RBX, add them as integers, and then store the result in RAX. Questions about this? So you can see we kind of have to learn the Intel as we go along. This is the semantics in a C-like language for addition in the Intel world, just to show you that the second operand is the destination. So it's the left operand of the addition and the destination. So that's just to keep reminding you about the confusing parts of AT&T assembly syntax. Questions on this? Okay, hopefully it means it's pretty straightforward. All right, subtraction is similar. So subtraction, same thing. The destination is RAX. Okay, so a little quiz on assembly arithmetic. So if I've got move immediate 9 into RAX, move 5 into RBX, and I say add RAX, RBX, what's the result of this addition? 14. Okay, what about this one here where I have the same two settings for RAX and RBX, but instead I add RBX, RAX. I swap these operands. What's the result of the 14? Still 14, right? What about for subtraction if I do the same thing? If I do subtraction here, I say move 9 into RAX, move 5 into RBX, and then I say sub RAX first, RBX second. What is the result of this subtraction? Who says negative something? Who says positive something? So it's negative, right? Because RBX is the left operand of subtraction. So RBX had 5, and RAX is the right operand of the subtraction. So it's 5 minus 9, which is, I guess, negative 4. What about for this operation where I do the same 9 and 5 in RAX and RBX, but I subtract RBX comma RAX? Now I get 4, right? So just to remind you, the destination is the right operand. That also means that it's the left operand of the arithmetic operation. So just the thing to keep in mind when you're coding this up. All right, questions on addition and subtraction? Pretty straightforward, right? I think you've done this with MIPS. So multiplication is similar. IMult for integer multiplication as opposed to floating point. Okay, so with these three pieces where we can load variables from memory, where we can do constant values, we can do store variables into memory, and we can do arithmetic, we can now translate this simple IR program by hand into machine code. So remember, these are the offsets for X, A, and B. You'll just look this up in a simple table. So there are 3 steps to doing, so actually I'm just going to do this operation here, X equals A plus B. So there are 3 steps to translating this. We have to load the variable data into registers, perform the actual arithmetic, and then store the result back into memory. So that's what X equals A plus B means at the architecture level, or at least one way to interpret it at the architecture level. Questions about this? Questions on how we're doing this? All right. So here's what the assembly code will look like. Here's loading A and B into registers. So this is the load operation that we saw. This is where we can find A's address in memory. This is where we can find B's address in memory, and we store them into registers RAX and RBX. Here's our addition. We are adding RAX to RBX and storing the result in RAX. That's the semantics of the AT&T syntax x86 add instruction. And then finally, we store the result, which is now in RAX, the result in RAX. We store it into the address for X, which is given by this operand. Questions on this? So there's our first translation. So X equals A plus B in this program can be translated to an equivalent assembly program with these instructions. Questions? Questions on that? So your compiler will see, so your compiler won't just spit out this code. It will have to see what variables are being used, translate to the correct offsets for RBP, and then generate this code for any input to the language. So whether it's add or subtract or multiply or divide or modulo, and for any operands. But otherwise, your code, your compiler will, at least the simplest version of your compiler, will always print out code that looks like this. You'll just substitute the operands and the operation for different operands and operation. Yeah, you had a question?
So real quick, RAX is the accumulator, right?
It's the accumulator, but it's kind of like general purpose now in the Intel world. From when you're looking it up, it's the accumulator. But add can take any registers because, yeah, RAX is like general purpose now. There may be some operations where RAX is special purpose. Okay, so here's another case where we do x equals 7 plus b. Just show you another translation, x equals 7 plus b. Here, we're going to move, oh, there should be a minus there. Sorry about that. We're going to move 7 into RAX, load b into RBX, do the same addition, and then store the result back in x. So notice here that I still used register RAX. You could have put you could have changed this add instruction to use 7. I did it this way because the template is identical to the previous one we saw. So this is like your template code. You just have to swap out these 4 parts in order to have a general purpose compiler for arithmetic. Questions on this? Questions on this example? Is this too easy, too hard? Can't tell yet. So yeah, the actual translation by hand is not too bad. But remember, we're writing a compiler that's going to do this translation automatically. It's going to have to not print out 7 plus x directly. It's going to have to look at the input and see which variable the user is asking for addition for, or subtraction, and look at what operation they're doing. Okay, division is a little bit more annoying in the x86 world. So this does use special purpose registers. So RAX always holds the numerator in Intel's integer division. So this is a case where RAX is a special purpose register. The denominator can be any register. So here we're moving 9 into RAX as the numerator, 5 into RBX as the denominator. In this operation, you kind of have to run this. This will, oh God, I can't remember what this stands for anymore now. But it will effectively sign extend RAX. So in the Intel world, division has a 128-bit numerator and a 64-bit denominator. That's the architecture they provide. So there are no 128-bit registers, at least not for the general purpose ones. So the way Intel solved this is you put your numerator, split that 128-bit number into 2 registers. This is very old-fashioned, register splitting stuff. You'll see this in lots of different architectures where multiple registers are used for one value. But for our purposes, we're only doing 64-bit, so you'll just always move whatever the numerator is into RAX and CDQ to do this sign extension. And then notice here, our division only has a single operand. It only takes the divisor, the denominator. And for all calls to iDivision, the quotient, the result of the division will be in RAX, and the remainder will be in RDX, always. So you always put the numerator in RAX, and you always get the answer in RAX for division, and you always get the answer in RDX for the remainder. That sort of makes sense? Questions? So it's just the idiosyncrasies of the x86 architecture. My guess is because to make a division work on all registers, there's probably a bunch of extra circuitry you have to do. So it's probably simpler to have division be hard-coded to one register. That's my guess. I'm not a computer architecture guy, but I'm guessing that's what it was. So division is used for both division and remainder. So how might this code change if we're trying to do remainder, modulo instead of division? What would change about how we use this code? Or would anything change in this code?
Can you repeat the question again?
Oh, so if we're doing division, if we're trying to translate division versus modulo, what, if anything, would change in this code or the usage of this code for division versus remainder? Yeah.
Just take RDX.
Yeah, you just take RDX. So the operation is identical because in the Intel world, the idiv integer division opcode always computes both the divisor and the quotient and the remainder every time. But in our language, there are 2 different operations. So if you're translating modulo, you do the same operations, but you take RDX because that holds the remainder. If you're doing division, then you take RAX because that holds the quotient. Questions on that? Questions on that? So this kind of illustrates the translation problem, the map territory problem, where the meaning of modulo doesn't have any intrinsic meaning by itself. We're giving it meaning by translating it to assembly code. And assembly code has its own idiosyncrasies, has its own semantics. And so we as a compiler writer need to make sure those things match so that our input language and our output program match. They're equivalent. Okay, so here's an example of, full example of division. So again, we've got local variables x, a, and b. A equals 9, b equals 5, x equals a divided by b, and then return x. So we're just going to show the translation of x equals a divided by b here. So just like with all the arithmetic operations we saw, we're going to set up the operands. We're going to load a and b into RAX and RBX. Then perform the division. So remember the CDQ, you just do that to get that 128-bit value and split across two registers. We call division on RBX because so why is RAX not specified here in IDiv? Why is it one operand? What was that? Yeah, it's the way, so x86 hard codes RAX as always being the numerator of the I division operation. So you have to put your numerator in RAX. And then you call integer division for RBX, which is where we set up our denominator. And then to save the result of the division, we take RAX, which holds the quotient, and we store it into the address of x. Questions on that? So very, very close to addition, except we use these operations instead. All right, how would modulo change? Somebody already answered it. So for modulo, in the original one, we took RAX, which holds the quotient, and stored it into our assignment variable, which is x. But in the remainder one, we just take RDX instead. So everything's identical, except we just use RDX. That's the value we store into the address for x. Questions? Questions on this? Does it seem simple? Seems almost too simple? Well, compiler is deceptively simple. So remember, you're writing code that will generate this assembly code. You're not actually sitting here doing the translations. That would be very easy, I think, for you guys. The tricky part here is that we're spitting out code. We're spitting out assembly code automatically. Or we're writing a program that writes out assembly code. So your program will have to correctly write out assembly code that matches the meaning of the input program. All right, questions on arithmetic and assembly, or its translation from simple IR? Okay, let's take a look at the project. So using Git, just like before, I just point you to the VC exercise. This is what the repo names will look like. Make sure copying these is easier to make sure you don't make mistakes. A brief on how you can set up your repo in Git. There's a project template here. It's kind of like into post, where it gives you a grammar and gives you the where is this? I'll go in here. So we'll give you, actually, let me do it this way. Let me start fresh so you can see what this looks like. Uh-oh. So here's the project directory, and I'm going to download the project template so I can walk you through what that looks like. I'm going to unpack it. These are the files you're going to get. So it's a pre-built parser. So all this code, most of this code is around parsing the input language for you, kind of like that thing you hand wrote for Bash. And then I've given you a template for codegen.cpp. So you can just move that into the file that you're going to submit. So here's the code you're given. It should look hopefully a little familiar from the Into Post project. But the difference here is that we've got a lot more language constructs. So instead of each operation, in the arithmetic operation, we have all of the statements that you can say in simple IR. Looks a little bit like a lot, but it's not that bad. So you can enter the entire file. When you say function and the name of the function, when you say end function, when you say local variables, when you say parameters, when you say return, etc. So all these, here you'll fill in the code that you run whenever you see those statements. So for instance, for our operations, our arithmetic operations, they go in enter operation. And this is where you're going to write code that's going to generate that assembly. So you're literally going to write string output code that's just going to spit out the text of assembly code whenever you see the operation. Does it kind of make sense? So you just fill in what's going to happen when you see each of those constructs in the input language. Okay, so that's your code template. To build it, as usual, we use make files to build it. This is going to run through and build it for you. And it's going to give you the CodeGen binary. So it's called CodeGen in, I guess, what is it called? Not camel case. The one where it's camel case, but it starts with a caps letter. I can't remember what it's called. Capitalized. It takes a simple IR program from standard in. Whoops. Takes a program from standard in, or you can also pass it a file as the first argument. Right now it does nothing, so there's no code written yet for any of these semantic actions, any of the functions that run whenever you see whenever the parser sees one of the constructs in the language. So yeah, classic self-check stuff. Okay, so for each project, I'm going to give you a list of which functions need to be implemented for that part of the project. So we're going to break down the compiler project into 3 parts. The first one, this is where you're going to implement enter operation, which is your arithmetic stuff, and the branching stuff. So how do you translate a label? How do you translate goto? How do you translate if goto? Now, a bunch of code is given to you already. So I've given you processing for the file as a whole, so that the assembly template stuff. I've given you the code that creates that layout in memory of your local variables and the symbol table. And I've also given you an example of assignment. So let me actually show this. So I copied all this example code already into my project. So let's, and we get nicer highlighting in Emacs. So let's take a look at what each of these do. Enter unit, this is just assembly file formatting stuff. You don't have to worry about this. This is just given to you. Local variables is a little complicated. It's computing all the offsets for all of your local variables. Again, you don't have to worry about it. You're just going to use it. But enter assign gives you a good example of the kind of code that you're going to write for completing this project. Okay, has anyone ever programmed C++ before? Anyone done C++? Okay, not many. So I don't expect you to be an expert at C++ here. I've given you the template already. There's only a couple of small differences from C that you'll need to use for this class. And I'm going to give you all of the things you need to say in C++ for this class. So the first one is writing the standard out. So in C, you would typically use printf, or maybe syscalls to do it. In C++, we have a slightly easier to use tool called cout. And the operator is double left angle bracket. So if you want to say hello world, this is what it looks like. You say cout, the double angle bracket operator, the string you want to print, and then endl is just a variable that holds the new line character for you. You don't have to do it exactly that way, but This is the kind of conventional way to do it. And here's an example of spitting out an assembly language comment. Questions on this? So just slightly different syntax for doing effectively what printf does. And yeah, okay, so we can see this in the given implementation of enter assign. You can see here that I'm saying cout, and then just like in printf, we can put escape characters. Has anyone ever seen /t instead of /n? What is /t? It's a tab space. It's just another kind of white space. So this is saying /tab because just by convention, assembly files are tab indented. This is just going to print out an assembly language comment. And then here, this is, don't worry yet about the syntax of it, but this is a value. This is the result of a function call. So this is how we're going to access parts of the syntax tree. And then we print out 2, and then that same thing. The next line, we're printing out a move operation here. You don't have to surround this with tab. We're not going to check white space. I just like it to look, a little nicer in the output. But this is printing out literally the text MOV, and then it's printing out this operand, which is like the variable name, and printing out comma RAX. So in general, what does this line do, or what kind of assembly code does this generate? What operations does this generate? It's a move operation, right? It's turning into a move operation. Yeah, sorry, no trick questions, no trick questions. And this operand, I've given you code that will actually give you the assembly argument for dealing with those variable offsets. So you're not going to have to do any heavy lifting for that. I've given you a function that will take a variable name and give you the exact assembly language operand you need to use for it. So you just give the variable name, and it will give you the assembly language operand you need for that. And so what is assignment? Assignment is just taking one variable and storing it in another variable. So here we're taking one operand and storing it in RAX, and then moving RAX into the offset for the destination variable. Actually, I probably could have used operand for a string for that. Yeah, I should have just used operand to string for that. It's the same thing. Okay, so that's the enter assignment code I've given you. So those are the ones given to you. So let's take a look at what the output of this program will look like. Let me remove the... So let me go through actually filling out these given functions for you. So here's enter unit. Oops. There's enter unit. Here's enter local variables. Don't worry too much about the exact contents of this one, and then enter assign. Doing indenting. All right, so I'm going to build this and then now run with some, I think I have this test case here. So it doesn't really do very much because all it does is print out the, doesn't have any variables or anything, but let's try assigning to 1 and see what happens. So here's my IR program. And now we've already got code that will, or we already have a compiler that will start spitting out assembly code. right? And it looks just like the assembly code we saw in our translation. So this is the allocation of space for local variables. Don't worry about that yet. But you can see this is the exact code that we'd expect for assignment. We see taking the operand 1, storing it into a register, and taking that register and storing it into the memory location associated with X. That sort of makes sense? So this is the compilation of one program. The compiler is code that describes how to translate all programs. So this is the code that will translate any assignment statement. And when we run it, and all it really does, it's really just like a template. It just takes whatever the right-hand operand was and replaces it with the store into RBP for the left operand, for the destination of it. So you can think of this as just like template code, something like this, where an assignment instruction is move from whatever the operand was to RAX, followed by another move from RAX to whatever the offset is into RBP. So here, operand and offset are the parts that change for different input programs, whereas the rest of it never changes for any input for any assignment statement, the input. That sort of makes sense? Kind of makes sense? So the thing you kind of have to wrap your head around is just using C++ and getting used to the syntax of it, and how to use the Antler parser generator to get the information from the input language. So these are, you guys learned Java, right? Did you guys learn Java, CS2? Or is that not, it's not required for this class, is it? It's not required. So, what's that? Object-oriented. Oh, that's required, right? All right, perfect. So you've all done Java. This is the C way of doing object dereferences. So imagine replacing this with dot in Java, the arrow, instead of the arrow. It looks a lot like the struct dereference field allocation. It's equivalent to Java's dot. In Java, everything's a reference. In C, C++, you can decide what's a reference or not, but this is the same thing in Java as saying dot. So this CTX, this is the parse tree. This is the syntax tree. And operand is the name of the node in the syntax tree, and getText just turns it into a string for you to print out. So this is literally just taking the text of the input, that value 1, I think that's what I had, value 1, and just spitting it back out in assembly. So all this C++ code is just a longer way of saying this template. Okay, that's the code given to you. So for this assignment, you'll have to write the compiler code for operations. So let's go back to the project. So all of the instructions and details for implementing the compiler are in this code generation project handbook. And there's a handy table here which will give you information on how to implement each of these functions. So here's enter operation that we need to implement for this project. And it'll tell you exactly what C++ object reference you need to use in order to get each piece of the input. So the destination variable can be found here by using this object reference. The left operand can be found here. This is operand 1. The second operand can be found here, and the operator itself can be found here. And then I give you how to, so this is the actual use of it. I give you how to do matching against which operator it is. So you take these operator names and match it against the operator given to you in the input. Questions on that? So this will look really very similar to getAssign. So you can use that given function as an illustration of writing these compiler functions, and then just extend it so that you have different, you actually output the arithmetic operation. So you're going to load 2 operands like we showed in class, spit out the corresponding operation, and then store the result back into memory, just like we did for enter assign. Questions on that? Okay, so I'm seeing. Okay, so it's, at least some people. I think there's some understanding here. Hopefully. All right. So one other little wrinkle is that recall that in C, which part of your C program starts running when your C program is executed by the loader, by the operating system loader. How does the operating system loader know where to start running your C program? So you have this big C file, it could have tons of functions in it. How does it know where to start running? Runs main, right? And so main is just a function, just like any other function. Remember we talked about the linker. The compiler doesn't care what's main. It just translates functions. So it's the same thing we have to deal with in our language. So we have to define a main function. So that's why every simple IR program is a function. So even this test IR, we have to declare a function main. So that means in order to run this program, we need to be able to create a function. Now, that's not until CodeGen 3, because that's really the hardest one. That one is the trickiest thing to generate. So I've given you hard-coded compiler functions or compiler implementations for generating one particular function. So this will make a little more sense when we get farther along into translating functions. But the only thing you need to remember operationally is these functions here, you just have to hard code the implementation I give you for these first two projects. So that way you don't have to worry about memory allocation, you don't have to worry about the base pointer, function calls, function returns. So it's tricky to get that stuff right. So to separate that out, I've given you hard-coded versions of these functions. And what these do is they basically take the assembly language translation of this one program and hard code that into functions. So for instance, for the return statement, the return value is always passed via RAX. This is just how the system defines how the application binary interface. So the hard-coded version of the enter return statement function always returns 0. So it always takes 0 and returns that value. Now that's not going to be true in all simple IR programs. That's only going to be true for this particular simple IR program. So what I've done is I've taken the translation of that and hard-coded it into the compiler implementation. So you just have to copy these functions. That's it. You just copy them, and then you will have a valid translation for this simple IR program. And all of your arithmetic and branching and pointer operations, you can just put that in here, and then your functions will take over and translate those. Does that sort of make sense? So it's a little annoying to deal with, but it means that you can work on each of these projects independently. It means that even if you mess up something on one part of the project, it won't affect the other project, because the whole compiler has to work correctly for even the simpler programs to work. So this is a way to just isolate out just arithmetic and branching, and you do it by you just follow the directions here. So it goes over doing this, but it's at the end it kind of walks you through explaining it, but you just literally copy these functions and use them in the implementation for CodeGen 1 and CodeGen 2. And then when you want to do testing, you start with this as your template. And I've even given you code to run these template examples. This sort of makes sense? So let me show you what it looks like when you actually use these hard-coded templates. Here's our template. This is our IO library that we're going to link with. And then this is code to do the translation. So this is the output of the assembly file with all of our hard-coded code for implementing functions. So you don't have to worry about any of what this code means. Just look for, if you want to add say assignment. Actually, do I have assignment in here already? Got 1 minute. So I can add the code you want to test here. So let's say I want to add assigning A to, or I want to assign result to 5, and I want to test assignment. Then here is the code that does that assignment. And then we can still build and run this code. So here's what it looks like to build it, and we can run it, and now we can actually see that 5 is being output instead of 0 because we assigned result to 5. All right, that's 1:15. So let me know if you have any questions. I got office hours after this, remember. Let me know if you have attendance questions, and yeah, have a good one. Have a good weekend.